All right, looking at empirical and molecular formulas for today. So we're going to be looking at what they are, how to calculate them, all that good stuff. All right, starting with what they are. Empirical formula. Formula that shows the smallest whole number ratio of elements in a covalent compound. So this would be something we also call a molecule, where they're doing sharing of electrons. The smallest whole number ratio is the empirical formula. And technically all ionic compounds are written as empirical formulas because they are the lowest ratio of the ions involved. But for covalent compounds, that is not always the case. So that's why we have this separate empirical formula that we find for molecular compounds or covalently bonded compounds. Because the molecular formula is the actual number of atoms of each element in there. For example, glucose. You guys all remember glucose from biology. The molecular formula would be C6H12O6 because that's the actual number of atoms in a molecule of glucose. However, its empirical formula is actually CH2O. That would be the lowest number ratio here because remember, these would all be able to be divided by a common factor of 6. And if you did that, the ratio would be 1 to 2 to 1 here. So we would write the empirical as the lowest ratio formula of them. So really all you have to do is look for a common factor that you can reduce them, and then you can find the empirical formula. Let's do some practice here. That first one, H2O2, that's hydrogen peroxide. You know, you put that stuff on cuts and things. It's a good cleaner. So what would be the empirical formula for that molecular formula? What would we divide them both by? Yes, it would be HO, because both of these are divisible by 2. So I'm going to erase that, sorry. Divide them both by 2, and yes, the empirical formula would just be HO. How about dinitrogen hexoxide here? What's the common factor with them? It's a 2, so if we divide them both by 2, we should get NO3. How about C2O3, dicarbon trioxide? What's the empirical formula for that one? This one's the tricky one. Yes, it's the same. It goes right here. Sometimes they are the same. If they don't reduce, they end up being the same. In that particular case, it is the same because you can't reduce it any farther. All right, number 4 is glucose. We kind of already went over that one, CH2O. How about this one? This one's called pentene. Yes. Divide them both by 5. Divide them both by 5, and you end up with CH2. How about diphosphorus octoxide? That's a mouthful. That's going to be PO4, exactly right. And then how about this nitrogen with hydrogen compound? Yes, NH4. Very good. Very, very good. Okay, so could give you a simple problem where you just reduce it. That's fine. Could also give you the picture of the bonded atoms, and these are both organic molecules, but you want to find the molecular empirical formulas from the picture. And then, of course, over here gives you the order to put them in: C, then H, then O. And then for the second one, C, then H, then N, then O. Now, it will specify which order for you to follow by the picture, or in a problem, it will list them in order of how they want you to write the formula. So looking at A, how do I find the molecular formula for A up here? What do I have to do? I should start with which letter? Which element? I need to start with carbon. And then all I need to do is start counting them. 1, 2, 3, 4, 5, 6. C6, 6 carbons. The next one, of course, is hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? 11, 12. And then 2 oxygens, O2. So this is going to be my molecular formula. Now, in order to find the empirical formula, all I need to do is divide them all by what? 2. Yeah, so this is C3H6O. That would be the empirical formula. Now you try B real quick. Follow this order that's given to you. CHNO. Start there, do your counting. And so will I. 1, 2, 3. C6H14 N4O2. That would be the molecular formula. Now all I have to do is reduce it. So reducible by 2, so C3H7N2O would be my empirical formula. So there we have our answers, and you can go back and review this as needed. Now, when we're calculating to find empirical formulas from percents, sometimes in problems they give you a list of, it had this percentage. They throw it into a machine called a spectrophotometer, and it can tell how many, like how much of each element is in there, and then it spits out the percentage, so then you know how to calculate it. So you could put a sample in the machine and then it tells you the percentage of each one. So we're going to follow these steps in order to calculate it. And it kind of goes with a rhyme. And I'm going to go individually through each step as we work the problem. The first one is percent to mass. So basically, if you get a percent, you just change it to grams, because we're going to assume it's a 100-gram sample because of 100%. Mass to mole. Okay, so percent to mass, mass to mole. That means we have to convert the masses to moles using the molar masses off the periodic table. We divide by small. Now, when we're talking about small, we're talking about the smallest mole value that we got in number 2. And then we multiply until whole, meaning we have whole numbers. Now, sometimes you'll get all whole numbers as your answer, and then you don't have to do number 4. Sometimes you won't, though. Common multipliers you might see, things that come out 3, things that come out 0.5, 0.25, 0.66, 0.20, 0.75. And these are the ones you'd want to multiply by. Like to make 0.33 a whole number, we would multiply it by 3. To make 2 a whole, 0.5 a whole number, you multiply it by 2. Obviously, 0.25 you would multiply by 4. 0.66 would give you, you'd have to multiply it by 3. 0.2, multiply that by 5, and then 0.75 if you multiply by 4. Your end result will be a whole number. So we don't want any decimal numbers like that. We want to make sure they come out all whole numbers. When we get those whole numbers, those become the subscripts of our empirical formula. So all this calculating is just giving us the simple formula. Let's do a problem. Looking here, an unknown organic compound contains 75% or 75.42% carbon. So we're going to do carbon first. Then this amount of hydrogen, hydrogen second, then nitrogen, and then oxygen. Determine the empirical formula of the compound. Well, the best and easiest way to keep track of all the calculations is to do a table or chart. So I put one in here for you, and I also put this in the choice board assignment to help you. First step, percent to mass, okay? So all you have to do is rewrite it over here as grams. Rewrite it over here as grams. Put it in the order that was listed in the problem. Change that to grams. Change this one to grams too. All right, so that's the percent to mass. That was step 1, percent to mass. Now we're going to do mass to moles, and this is where we're going to do our T-charts. We're going to draw them in here. So we're going to put the grams down here and the 1 mole on the top. If you go look it up on the periodic table, you would see that carbon is 12.01. That's the molar mass of carbon. So we're doing kind of our mini T-charts in here inside the chart itself. So the grams for hydrogen, that's 1.01 on the periodic table, equals 1 mole. And then nitrogen, this is going to be 14.01 grams, equals 1 mole. If you look at your periodic table, you would notice that value. And then, of course, most of you probably already have oxygen memorized. What's the molar mass of oxygen? Anyone? We're going to have that one memorized by now? Come on, that one's easy. 16, yes, exactly right. 16 grams, very good. Now we calculate the moles for each one of these. So we kind of throw our T-charts in there. We do 75.42 divided by 12.01. Now we're going to carry this out 4 digits because this original percent was 4. So 6.280, 6.63 divided by 1.01. For hydrogen, this one's 6.56. Then we have 8.38 divided by 14.01 for the nitrogen, 0.598, and then 9.57 divided by 16, which is also 0.598. Now, that was step 2. We changed them to moles. Very good. Now, step 3 is divide by small. Which mole out of these 4 is the smallest? So which one do we need to use? Divide by small. Which one's the smallest? The 6.28, the 6.56, 0.598, or 0.598. These two happen to be the same. Yes, both of these are the smallest. So we're going to divide everybody by this number. Divide by the 5.98, or you can use the slash, whichever is easier for you. Divide everybody by that smallest mole number. Now, you know, this is going to be a 1. This one's going to be a 1 because you're dividing it by the same number. That's easy. But let's look at this one. 6.56 divided by 0.598. Well, if you look here, it's giving us 10.96, but we round this up. So that's basically 11. Okay, so that one's really close to the whole number we just rounded up in that case. And then 6.28 divided by 0.598, and we get this one is 10.50, like that, exactly. Now, are all 4 of these already a whole number? No, this one right here is not a whole number. So now we have to multiply to a whole. And 0.5, what do we multiply in order to make this a whole number? 2. So we multiply this one by 2, but we have to do it through everything. So everybody gets multiplied by 2 now. So this becomes a 2, this becomes a 2, this becomes 22, and this becomes 21. Now these are going to be our subscripts. So this is going to be C21, because remember the first one's carbon. Second one's hydrogen. So that's 22 here. Third one's nitrogen. That's a 2. And then the fourth one, oxygen, gets a 2. This is our empirical formula. All that calculating just to find that. Here's a nice cleaner version. All the numbers in there. You're welcome to go back and, you know, absorb it. This one may need, you know, some processing time and marinating and looking at it again. One more thing we can figure out is the molecular formula. Once we know the empirical formula, we can find the molecular formula if they give us the molar mass of the molecular formula. So calculating molecular formula, we find something called the multiplying factor, or N. And the way to do that is to take the molar mass of the molecular formula, which they should give you in the problem, by the way, divide it by the molar mass of the empirical formula, which either you just found or it's also in the problem. That gives you a multiplying factor. And this should be a whole number too, by the way. When you get that, it's going to be a multiplying factor number that's whole. So you take the empirical formula subscripts, multiply it by the multiplying factor, and you'll get your molecular formula. So what does that look like? Let's take a look at that. Exercise 3 is showing us this type of problem. Let's go back to red. All right. Determine the molecular formula for a compound OF2 that has a molar mass of 215.10 grams per mole. Well, this is obviously an empirical formula because it's in its reduced form. OF2, you can't reduce that anymore. So we have this is our molar mass of the molecular formula. Okay, now we just have to find the empirical formula's molar mass. So O is 16 off the periodic table, we know that. F 2 times, and then if you look at the periodic table, you'll see that it's 19 each. Okay, so that's 38 plus 16, which happens to be 54 grams per mole. So this is my molar mass of my empirical formula. So all I have to do is take this, the molar mass of the molecular, which is going to be the bigger number, of course, divide it by the empirical formula's mass, and I should get my multiplying factor N. We divide these two numbers right here, what you'll see, put that into your calculator, you should get 4, or right around 4. I think it was like 3.98 something, which will round up to 4. It's very, very close to that whole number, you just rounded up. So what do I do with this? Then I take my OF2 here and I multiply everything by 4. So this is like an understood 1. So it becomes O4, and then 4 times 2, the F is an 8. So this is going to be my molecular formula. So once you get the empirical formula, if you know the molecular formula's mass, you can calculate the multiplying factor, multiply it through, and get your molecular formula, which obviously is not the reduced form because O4F8 is reducible. All right, last example here. If they don't give you percents, but they give you gram samples instead, like we shoved it in the machine, this is how many grams we got of each element. Same idea, except for you get to skip step 1. It's now mass to mole. You just go right to mass to mole. You skip the percent part. Divide by small and multiply till whole, still in there. You're going to follow the same steps except for you skip number 1. Skip step number 1. And the common multipliers still apply. And they're still going to be the subscripts of the empirical formula. So let's do an example. This one's going to have us also do the molecular formula as well in part B. So we have an A and a B part. So we have this sample that was thrown in the machine of an unknown organic compound. It was analyzed and found to contain carbon, hydrogen, and oxygen, a certain amount of grams of each. All right, so we're going to start by finding the empirical formula. Of course, we're going to use the chart. Now it tells us right here that our molar mass is 456.5. So later on, we're going to use that to find part B. First thing to do is set up your table. You get to skip the percent part. You go straight to mass. Okay, I'm going to write this up here, the 456.5 grams per mole, though, because I'll forget that number. This is my molar mass of the molecular. All right, we'll need that later. But we're gonna go ahead, gotta change them to moles, and carbon is still 12.01 grams equals 1 mole off the periodic table. Hydrogen, of course, is still 1.01 grams per 1 mole, and oxygen is still 16 grams per 1 mole. So you're skipping the percent step, you go straight to changing it to moles. 2.77 divided by 12.01. This one I'm going to go out 4 digits because this is 4, so 0.2306. 2.33 divided by 1.01 for hydrogen. This is 0.231. 3 digits because this one only goes out 3 digits. And then 1.384 divided by 16. I'm going to carry this one out 4. So this is 0.08650. 4 digits. I added the O on the end. Out of those 3 numbers, which one's the smallest? What do I divide everybody by? Which mole value, the carbon, the hydrogen, or oxygen was the smallest? Yeah, the oxygen. So we're going to divide everybody by, I'm just going to do it this way. So I only have to write it once. Everybody gets divided by this number. So this one becomes a 1. That's pretty easy. 0.231 divided by 0.0865. This is about 2.67. And then this one up here, 0.2306 divided by 0.865, excuse me. And this one is 2.666. Notice these ones aren't whole numbers. We need to multiply through. What are we going to multiply through by? What's a 6766 kind of thing? What's the multiplier for that one? 6, we're going to multiply everything through by 3. That's a common multiplier there. So this becomes a 3. If you do 2.67 times 3, it's going to be right around 8. That's going to be your whole number here. So this one also would be an 8. So our empirical formula is going to be C8H8O3. That's the empirical formula. We found our subscripts. Now, in order to find the molecular formula, we need to take our molecular formula and we need to divide it by this one's mass, the molar mass of the empirical. Well, we've got 12.01 times 8 plus 8 times 1.01 and 3 times 16. So 3 times 16, we add all that up. Use your calculator, and we'll get our empirical formula's mass. And this happens to be 152.16. Here we're going to be able to find our N value, 256.5 divided by 152.16. Oh, and that's approximately a 3. N equals 3, right? Did I do that right? So the multiplying factor then should be C 24, right? Because 3 times 8 is 24, H 24, and then O 9. And that would be our molecular, don't need 2 M's here, molecular formula. So these are long problems, but there's only a couple for you to do. Use the chart. It's the easiest way to follow in the steps of the rhyme. And then you should be able to come up with your subscripts for your formula.